Welcome to True Projects. In this video, we are going to explain about the project title Multi-Class Stress Detection Through Heart Rate Variability, a deep neural network based study. Before diving into the execution, let me give you an overview of the project. Stress is the body's natural response to change, whether physical, emotional, or mental, serving as a mechanism for adaptation and protection. While moderate stress can enhance focus and alertness, chronic stress poses significant health risk, contributing to conditions such as anxiety, depression, and cardiovascular diseases. Traditional stress detection methods such as self reported questionnaires and physiological measures like heart rate, blood pressure, and cortisol levels are limited by biases, inaccuracies, invasiveness, and the need for specialized equipment, making continuous monitoring impractical. To overcome these limitations, the proposed system utilizes deep learning algorithms, including 1D CNN, that is convolutional neural network, 3D CNN, LSTM, long short term memory, GRU, gated recurrent unit, and hybrid model, which contains LSTM plus GRU plus RNN within a structured workflow covering dataset importing, exploratory data analysis, visualization, and feature selection to improve stress detection accuracy via HRV, heart rate variability data analysis, providing a comprehensive solution for multi-class stress detection. This project benefits individuals through continuous stress monitoring and healthcare providers with improved diagnosis and treatment. Employers gain enhanced workplace wellness and productivity, while researchers receive reliable data for stress studies. We integrated Flask to deploy the project, creating a web application that allows users to upload HRV data, process it through our deep learning models, and receive stress level classifications, ensuring easy online accessibility. To implement this project, we need software and hardware requirements. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Algorithms used. These are the algorithms built in the project for stress detection through heart rate variability, which are 1D CNN, that is 1D convolutional neural network, 3D convolutional neural network, LSTM, long short term memory, GRU, gated recurrent unit, and a hybrid model which combines LSTM, that is long short term memory, plus GRU, gated recurrent unit, plus RNN, recurrent neural network. We have built all these algorithms to compare the performance with different evaluation metrics like accuracy, precision, recall, and FN score. And here the LSTM, that is long short term memory, outperformed the other algorithms, and that is the reason we have deployed it in the front end. Now let us execute the project. To execute this project, first we need to open the code folder, which contains the project source code files. So here, this is the HRV dataset. In this project, we have utilized the heart rate variability dataset. So in this folder, we are having the HRV dataset. Let us open this. So here, this is the final dataset. So the dataset is split into test and train. Let us open the test file. So here, these are the different features: mean RR, median RR, SDRR, RMSSD, SDSD, SDRR, RMSSD, HR, that is heart rate, PNN 25, PNN 50, SD1, SD2, CURD, Q, mean REL RR, and many more. So these features are used to detect stress. So here we can see the column for the condition. So here we can see we are having no stress, time pressure, interruption. So these are the different labels. So this data set is used to evaluate the performance of the models. Now let us close this. And here this is the train data set. Let us open the train data set. So here also we can see the different features, which are mean RR, median RR, SDRR, RMSSD, SDSD, SDRR, RMSSD, HR, heart rate, PNN25, PNN50, SD1, SD2, Kurtz, Q, and many other features. And here we can see the target column in which we have the different labels, which are no stress, interruption, and time pressure. So based on these features, we will detect stress, and this data set is used to train the models. Let us close this. And here we have the raw data set also. This is the model folder which contains .hy files. These files contain algorithm information which will be loaded into the project code during runtime. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And this is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And here, this is a sample data set. Let us open this. So here, this is the sample data set which we will use during the execution. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. So if we are new users, we need to register first. So click on register link here. So here we need to enter all these details to register. But I have already registered. So click on login button here. So here we need to enter the username and the password, which are static, and then click on login button. We have logged in successfully and we are redirected to the prediction page. So here we need to enter the values of these parameters, and after entering the values, the application will predict whether stress is detected or not. These are the features extracted from heart rate variability data. Before entering the values, let us understand what these features are. So the first one is mean RR. Mean of RR intervals, time between successive heartbeats, a measure of average heart rate. Coming to the next one, which is median RR. Median of RR intervals, a measure of central tendency in heart rate variability. LFNU, normalized low frequency power, a frequency domain measure of heart rate variability associated with sympathetic nervous system activity. The next parameter is VLF, which is very low frequency power, another frequency domain measure of heart rate variability reflecting long term regulation mechanism. TP, which is total power, the sum of VLF, LF, and HF power representing overall heart rate variability. SDRR, RMSSD, RELRR. Ratio of the standard deviation of RR intervals to the root mean square of successive differences between RR intervals, a time domain measure of heart rate variability related to sympathetic parasympathetic balance. LFHF, ratio of low frequency to high frequency power indicative of sympathetic parasympathetic balance. SDSD, standard deviation of successive differences between RR intervals, a time domain measure of short-term HRV. SD1, which is short-term heart rate variability related to the dispersion of points along the line of identity in Poincare plots. RMSSD, root mean square of successive differences between adjacent RR intervals, a time domain measure of short-term heart rate variability. SAMPIN, sample entropy, a complexity measure of heart rate variability reflecting irregularity and unpredictability. PNN25, percentage of successive RR intervals differing by more than 25 ms, a measure of parasympathetic activity. VLF PCT, that is percentage of VLF power in total power, a relative measure of very low frequency power. SDRR, standard deviation of RR intervals, a time domain measure of overall HRV. ST2, that is long-term heart rate variability related to the spread of Poincare plot points perpendicular to the line of identity. So these parameters capture various aspects of heart rate variability, reflecting the complex interplay between sympathetic and parasympathetic nervous system activity and overall autonomic regulation. They serve as input features to the deep learning models for stress detection, leveraging the rich information contained in heart rate variability data to classify stress levels accurately. Now let us enter the values. So let us enter the values from the sample dataset, which I have shown you during the explanation of the code folder. So here, this is the sample dataset, which contains the test cases. And here, this is the target column in which we have the different labels. So here 0 is for no stress detected, 1 is for interruption detected, and 2 is for time pressure detected. Now let us enter the values. So here I'm entering the first values. So mean RR is 6.42E, median. So similarly, we will enter all these values from the test cases. So here I have entered all the values from the test cases here. Now click on submit button to get the prediction. So here we can see the result, that is no stress detected It means the HRV, that is heart rate variability data, shows patterns typical of relaxation or normalcy with no significant indicators of stress present. Now let us enter another set of parameters. So click on try again. So I'm entering the values again from the test cases itself. So now let us enter the second case here. So from the test cases, I'm entering the values again. So we need to copy all these values. So here I have entered all the values. Now click on submit button. So here we can see the result, that is interruption detected, which indicates the HRV, that is heart rate variability data, shows irregularities or sudden changes, suggesting a disruption possibly due to external factors, but not necessarily sustained stress. Now let us enter another set of parameters. Click on try again. So again from the test cases, I'm entering the parameters. So here I have entered another set of parameters from the test cases. Now click on submit button. So here we can see the result, that is time pressure detected. It means it shows the heart rate variability data indicating signs of acute stress related to time constraints such as decreased variability and increased heart rate. Now let us enter the set of parameters. Click on try again. So I'm entering the parameters again from the test cases. So here I have entered the features value. Now click on submit button. So here we can see the result, that is no stress detected. It means the HRV data, that is heart rate variability data, shows patterns typical of relaxation or normalcy with no significant indicators of stress present. In this way, we can enter more sets of parameters and check whether stress is detected or not. Now click on graphs link here. So here we can see the correlation of train data. So correlation tells us whether two variables are correlated or not. So here this is the correlation of the train data, and here we have the correlation of the test data as well. And here this is the pie chart which represents the target values, which are no stress, interruption and time pressure. And here we can see that the no stress is having the more percentage than interruption and time pressure. So this is the count of the target values in the training data. And here we again have one more pie chart for the count of the target values in the testing data. And here we have the comparison graphs. So the blue color represents accuracy, orange color represents recall, green color represents precision, and red color represents FN score. So here on the x-axis we have the algorithm name, and on the y-axis we have the score for the different evaluation metrics. So the algorithm which is performing best will be used for prediction. And here we have the individual comparison graphs of the evaluation metrics. So this is the recall comparison graph, and here we have the precision comparison graph, and this is the FN comparison graph. Now click on logout link. The project concludes that deep neural networks can accurately classify stress levels using heart rate variability HRV data. It successfully identifies no stress detected, interruption detected, and time pressure detected, demonstrating HRV's reliability as a stress biomarker. This enables precise stress monitoring and timely interventions, particularly in high stress environments, highlighting the potential for advanced stress detection systems to enhance health and productivity.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.